time we saw that the second law of Newton in general says sum of the forces applied to a particle of mass m is equal to time rate of change of this quantity called linear momentum, which is mass times velocity. And if mass does not change with respect to time, then you can simplify it to sum F equal ma. And then for a system of particles, it is going to be only external forces equals to the total mass of the system times acceleration of the center of mass. And we also learned that at the center, the acceleration that we should measure is always with respect to an inertial, or what we call Newtonian reference frame, which does not have acceleration itself. So now, throughout the rest of this chapter, we assume that the mass is constant, and so that sum F equal ma, we can decompose F, and we can decompose A along any set of axes that we desire. Okay, so if we do it along XYZ Cartesian, then we get the three formulas that we used last time for the describing the motion of the particle in Cartesian coordinate. But on the other hand, we could decompose the force and acceleration onto the Tn axes. And if there is a third dimension, we also can do it along the binormal axis. Okay, so then since these two vectors are equal on the left and right, then we get sum of the forces in the tangential direction is equal to mass times acceleration tangential. And we know that AT is what? Rate of change of speed. And then sum of the forces in the normal direction is mass times AN, and AN was V squared over rho, and rho was the radius of curvature. Again, if there is a third dimension, binormal, then we can have sum of the F in the binormal direction is mass times acceleration binormal. Okay, and actually we can use that over here in this problem too. So let's see how we use this in this example 14.8. So here we have a car that is going through a ramp and wants to basically either exit or enter some road, maybe exit the highway and enter some side road. And the radius of that curve for that ramp is 60 meters, and the static coefficient of friction between the road and the tire is 0.4. We want to know the max speed at which the vehicle can enter the ramp and keep moving along the ramp. Okay? So this is the aerial photo, the top view, as well as this one, zoomed in. And here is a front view, okay? So if you see here, the ET vector, unit vector, is tangent to the path. EN is normal to ET and toward the center of the curve. And if there is a binormal direction, which it is in this case, it is going to be perpendicular to both. And it's ET cross EN. So if ET and EN are the way they are, then EB, the binormal unit vector, is going to be downward, okay, perpendicular to the ground, downward. So it is the same direction as MG. Okay, so we have our three axes here. And I can also show that over here for you. So this is our car from the top view, right? And these are our unit vectors. So this is ET, tangent to the path in the direction of motion. This is EN toward the center of the curve. And then EB is, as I said, perpendicular because it's ET cross, right? Remember, EB is ET cross EN. So in this case, it is going to be perpendicular to the page and inward. So we have to show it with the cross, right? So here, this cross is going to be EB. or if you look from the front view, if this is the car from the front view, let me cheat here a little bit from the drawing. Yes, so if this is the front view of the car, right, then your unit vectors are like this. En is toward the center, EB is downward, and ET is perpendicular to the plane outward. So it's like this, right? You know, a circle with the dots means perpendicular to the view outward. So these are our unit vectors. So and we here showed our coordinate system that we're going to use, and then the forces, if we want to show them. Let's see what forces are applied to this car as it goes along the road. So clearly we always have mg, so no question about that. Then there is a normal force from the road on the tires, N, and then if you remember, if the speed is not equal to 0, if the speed is not, the derivative of the speed is not equal to 0, in other words, as you go along the ramp, you change your speed. You put your foot on the accelerator or on the brake. If that's the case, then there should be also a force in the t direction. And that, in general, as I said, can come from what? Can come from friction, right? We learned that wherever there is a contact, there are two forces, a normal force and a friction. Now, in this case, in general, your friction is not in the T or N, it's in both. So your friction in general can be something like this on the tire. And so it has a component like this and a component like that. So this is Ft and this is Fn. And this Ft is responsible for creating At, which means changing the speed. And this Fn is responsible for giving you the centripetal acceleration. So, sorry for the notification. So if we want to show them, in this case, the Ft is equal to 0, but in general, we can show it if we want to. So the force Fn is in this direction, and the force Ft is normal to the plane like this. Okay, so here we have shown free body diagram in both views, and we have also shown our coordinate system. Okay, and now, as I said, we have three equations of motion in general. So sum of the forces in the t direction is equal to mat, and at is what? Let me write it. It is dv over dt. Then sum Fn is equal to man, and an is v squared over rho, and then sum forces in the b direction is equal to mab. Okay, so these are the three general equations of motion for tangential normal by normal. Now, in this case, we assume that the guy is going to maintain a constant speed as he goes along the ramp. So here we assume, based on the problem, because it never said it can increase or decrease, we assume that v is what? Constant. Therefore, this term is equal to 0, and therefore there is no need for the longitudinal friction. In the b direction also, if you look, we have positive mg minus n. Note that here eb is downward positive. So it's going to be mg minus n is equal to upward or downward acceleration of the car, and here we don't assume that the car can lift off the road, Therefore, this term is equal to 0, and from here we can find n to be equal to mg. Now, in the tangential direction, we have f sub n in the positive is equal to mv squared over rho, and rho here is a constant radius of 60. Or if we want, let's just leave it as r, and then we're going to replace the number later. Okay, I just want to do it parametric so that you see what I'm doing. Now, it says what is the max acceleration that you can have, and if you want max velocity, I'm sorry, what is the max velocity that you can go through? So if you want max here for v, since m and r are constant, then when the right hand side is max, therefore the left hand side should be max, right? And the question is, when is it that you would get maximum friction? Based on what we know, the maximum friction a surface can generate is mu s times what? Times n. This is equal to mv max squared over r, right? And you know that we calculated n, correct? So we know what n is. N is mg. So if we replace, you're going to get mu s times mg is equal to mv max squared over r. And you clearly can simplify m. That's why the m was never given, because you don't need it. And if you solve for v max here, multiply both sides by r and then take the square root, it's going to be square root of r g mu s. In this case, you have mu s and you have r and you have g, so you can calculate the number, and we'll do that. But I just want you to see this important formula, which tells you that the maximum speed depends on which parameters? It depends on the radius, and it depends on what? Mu s. So clearly, the bigger the radius of the curve is, the faster it can go. And that's right? Because when the radius is too big, then basically you are turning so basically gently. Or in other words, this term here, because r here is in the denominator, the centripetal acceleration is going to get smaller, so you need a smaller force. So bigger radius allows you to turn faster if you want, or go faster. If it's infinitely big, then you're literally going on a flat road and you're not turning. There is no centripetal acceleration, so you can go as fast as you want as long as the friction allows. So r is determining, so if you're going on a sharp ramp, which is small radius r, don't go too fast. The other one is the static friction, right? The better the condition of friction is for that ramp, the faster it can go. But if there is wet road, okay, and you're going along a small ramp with a small radius, never go fast. Otherwise, you're going to be simply kicked out of the ramp and kill yourself probably. So this is really important. And again, if we plug in the numbers here, so we have 60, 9.81, and 0.4, right? And that is going to be 1534 meters per second. So you see how I'm going to solve a problem using t coordinates. Now, could I also do this problem in the xy coordinate? Yes. But then, if you remember the problem we solved in class, you have to deal with a ton of derivatives and chain rule. So sometimes the t coordinate gives you a lot of relief, and problem solving is significantly faster and easier. So we're going to solve more problems in the class. But now we want to also look at the second coordinate system we have, which is the cylindrical or 2D version of it, polar coordinate, and we try to solve problems in this coordinate system. Okay, so if we use cylindrical coordinates, because the path of the particle is best described by a radial distance, the angle theta, and maybe vertical motion z, then we can use this coordinate system. And so sum f equal ma again, but this time we are going to decompose f and a along r, theta, and z, and by setting the two vectors equal and their components equal, we're going to get three equations. One is along the radial direction. Sum of the radial forces is equal to mass acceleration radial, and we learned that acceleration radial is r double dot minus r theta dot squared or omega squared. In the transverse direction, sum f theta is equal to m theta, and a theta, if you remember, was r alpha plus 2r dot theta dot, right? Remember, this was the Coriolis acceleration. And then if there is a z, of course, in the z direction, we have sum fz equal maz, and az is z double dot, right? So in general, three equations. If it's 2D or polar, we just have fr and f theta. And you might wonder, okay, how do we use those to solve a problem? So let's look at problem 1499 of the textbook. Here you have a smooth bar rotating in a horizontal plane with constant omega of 60 rpm. Several words here. Smooth. Smooth means no friction. Horizontal plane, which means you're looking from the top view on this. Okay, so it's not a vertical pendulum or something. It is a bar that is rotating on a table, let's say. And here the omega is maintained at 60 rpm. The spring constant is 20 Newton, and when the length r, and r is the radial distance between this collar that is sliding on this bar, it's the radial distance between that and the origin, okay, the pivot point. When r is 3, then the spring is not stretched. So what is the situation right now when r is less than 3? Clearly we have stretched the spring. Now we want to know if when r is equal to 1, so spring is stretched significantly, 2 meters, at that point the radial velocity of this collar is 10 meters per second. You see v sub r, and v sub r, if you remember, in the cylindrical coordinate, v was what? V was r dot er plus r theta dot e theta plus z dot e z. So this is your radial velocity, Vr. This is your transverse velocity, V theta, and this is what? Vz. So it's talking about r dot. It says r dot, when r equals 1, it is equal to 10 meters per second. By the way, the mass of this guy is 1 kilogram. Now we want to know when r is reduced, so spring is pulling back and reducing the stretch. So r is 2, in other words, the spring is only stretched for 1 meter. How much is Vr? Okay, at r equal 2. So here we are going to, again, write what we know and we don't, draw the FBD, show the coordinate system, apply our equations, and if we have enough equations, we solve for the unknowns. So here it says theta dot is equal to 60 rpm, and it is constant. First of all, we convert rpm into standard units, so we multiply it by 2 pi over 60, so it is going to be 2 pi radian per second, and it is what? constant, which means theta double dot is equal to 0. Okay, so there is no theta double dot, and theta dot is 2 pi. Then it says that K is equal to 20 Newton per meter. Mass of the particle is 1 kilogram. At R equal 1, we have R dot equal 10, I assume, right? 10. We want to know at R equal 2, what is R dot? This is K, and by the way, it says spring is not stretched at R equal 3. So these are all of the knowns and unknowns of this problem. Now, we move on and we draw the free body diagram for the particle. Now here there is a rod, but the mass of that is not given, and we are not interested in the free body diagram of the rod, so all we care about at this point is the color. And here, instead of drawing two different views, I would draw a 3D view of it. So here, that's the center, this is the rod, and this guy here is that cylindrical color. Okay. Now, you might say, okay, what forces are applied on this color? Clearly, along the bar, there is no longitudinal force because that comes from friction, right? There is contact. This color has a mass, so there is mg. That's 1. It is connected to a spring, and it has contact with the bar. So we have contact forces and we have the spring force. First of all, let's look at the spring force. So the spring force, which is radially applied, is in which direction? Is it outward or inward? You know, at R equal 3, the spring is not stretched. When R gets less than 3, like 1 or 2 in general, then the spring is stretched, so it is going to pull back. Therefore, the spring force is radially outward. Now, the contact we have for the collar and the bar, as we said, there is no friction in that contact, but there is a normal force. Now, which direction is the normal force? Well, in this case, that normal force is in this general direction like this, because the contact is not right at the bottom of the collar. It's not exactly on the right side. It is actually somewhere between bottom and right. So it's somewhere like here. That's where the contact is happening, and normal to it is this n. So if we want to decompose that n, there is one component of it in basically the n direction, or here we call it the theta direction, and there is one component of that in the vertical direction. Okay, so this is like n1, this is like n2. These are the components of n. And n1 is necessary to counteract mg, so that this object does not go up and down because it is moving on a horizontal plane. And n2 is necessary to provide a theta. And fs provides acceleration in the r direction. Okay, so that is your FBD. Your coordinate system is r is radially outward, So this is ER. E theta is perpendicular to that, so E theta is in the same direction as N2, and then perpendicular to both, upward, is what? EZ. Okay? So this is your FBD, this is your free body, this is your coordinate system. Now, let's get to the equations. So the equations say that sum of the forces in the R direction, which is what in this case? Fs, right? And that's it, is equal to MAR, and AR is what? It is R double dot minus R theta dot squared. Then sum F theta is equal to, in this case, what we have is N2. This is equal to MA theta, and A theta is R theta double dot minus plus 2R dot theta dot. And finally, sum Fz, which in this case it is M1 minus Mg, is equal to MAZ, which is Z double dot. So I got my three equations, my governing equations. Now, how do we solve? What do we have? What do we need to find out in these equations? So in the Z direction, that's the easiest to look first. This guy is moving on a horizontal table, so it is not going to leave the horizontal plane. Therefore, this term is equal to 0, and therefore that component of n, which is n1, is equal to mg. Now, nobody asked for it, so yes, we could find n equal mg, n1, but it's not of any interest. In the theta direction, we have n2, and we have r theta double dot, and we know theta double dot is 0, and we have r dot and theta dot, so this gives us that n2 is equal to 2m r dot theta dot, and theta dot was 2 pi. So if I know r dot at any point, it gives me n2 at that point, but n2 is an unknown of the problem itself. So again, this is good if somebody asks you for N2 reaction, but here we don't care about it. Therefore, we are not going to bring it into the problem, because what we really need to find is R dot itself. And here we cannot find R dot from N2 because N2 is unknown. So that's not going to go anywhere. In the radial direction, however, the spring force, we have to first calculate it. We know the spring force, assuming it's a linear spring here, and assuming that the displacement is not too big, which is kind of it is. It's 1 meter, 2 meters, 3 meters here, but let's say, and k is not super big, but here, again, we assume that it's linear. So the magnitude of this is k times delta L, right? And delta L means what? Elongation from the unstretched position. How far have you elongated? And if I go back and look, elongation is what? The current length minus the unstretched length, absolute value of it. So what is the unstretched length of the spring? I don't know, but I know when R equals 3, it's not stretched. And when I make R smaller than the 3, then it starts getting stretched. So how much is the elongation? The difference between 3 and R, right? The difference between 3 and R is the elongation. Agreed? Because if R is 3, then there is no elongation. If R is less than 3, then there is elongation. So the stretch of the spring is what? 3. So let's make sure one more time. It says when, and the unstretched length of the spring is 3. Oh, okay. No, wait. Actually, this end of the spring is fixed. Okay? So the spring is between this radial distance 3 and the current location of the collar. So it says the spring is the unstretched length of a spring is 3. So, which means when the spring is extended all the way to here. Now, when this, I guess we read the problem wrong. When unstretched is actually, in this case, it's going to be compressed, not stretched. So spring is not elongated when it's expanding all the way to the pinpoint. And when R is less than that, so R is going to be the amount of elongation, then the spring actually is going to be compressed. The spring is going to be compressed. You are compressing it back because the current length is less than 3. So if we go back, then we have to change the direction of the spring force. Okay, so we read the problem wrong. The spring force is actually inward. And delta L in this case is R, so it is going to be K times R. So if we write it, now since ER is outward positive and FS is inward, it is going to be negative K times R, and K is 20 in this case. This is equal to M, and M is 1 unit, times R double dot minus R times theta dot squared. Okay? So now if you look at this equation, clearly there is no other unknown than R or R double dot or R dot in it. So first of all, this is a what? This is a differential equation. And it is second order, and the coefficients are all constant. So it's a second order constant coefficients ordinary differential equation with initial conditions, and we can easily solve this. So first thing we do, we bring everything to one side, or at least R double dot on one side and R's on the other side. So we're going to make it like R double dot is equal, if you take R's to the other side, it's going to be R times 4 pi squared minus 20, right? Because this is 4 pi squared minus 20, and if you calculate that number, right, 4 times pi minus 20, it is going to be 1948. So again, I took this term to this side, it becomes positive, and then subtract it from R. Okay, so this guy is 4 pi squared minus 20. And now that's all I have, a very simple second order ODE subjected to 2 initial conditions. What are those? Those are here. That at R equal 1, R dot is equal 10. So if we assume at the beginning R is 1 and R dot is 10, we say R at 0 is 1 and R dot at time 0 is 10. So second order, 2 initial conditions. We should be able to solve this based on what you learn in DiffyQ. Another way to solve this problem, since R dot is the one that is of interest, what I can do, I would apply the chain rule here, because this R double dot is an acceleration term, right? And if you remember in the past, one way we did acceleration when we wanted to get the time independent equation, right? Because here nobody cares about time. We wrote A, if you remember, we wrote it as V dV over ds, right? This is what we did when we wanted to do time-independent equation. In this case, I can easily show you that our double dot, which is d of r dot over dt, I write it as d of r dot over dr times d of r over dt. Right? I'm applying the chain rule. And this guy is what? R dot, so I can write it as r dot dr dot over dr, right? Which is v r dot dv dr dot over dr or ds. So I would write it as r dot dr dot over dr is equal to 19.48 times r. And what's good about this? Yes, you can do separation of variables. All you need is cross multiply both sides by dr. So you're going to get this one. Then you can integrate both sides. From initial r, which is 1, to the final r, which is 2. From initial r dot, which is 10, to the final r dot, which I don't know. And clearly the left hand side is integral of r dot dr dot, so it's going to be r dot squared over 2 minus 10 over 2, 10 squared over 2. This is going to be 19.48 over 2 r squared. So this is going to be 2 squared minus 1 squared, and if from all this you calculate your r dot is going to be 12.6. And that's the solution. So you see, now at any point, if we want to find the normal reaction, if somebody says, what is the normal reaction at, let's say, r equal 2? When r is equal 2, what is the normal reaction between the color and the bar? You come here, you plug in that r dot here, it gives you n2. n1 is always constant, and then the magnitude of the actual normal force n is equal to what? Square root and 1 squared, right? Because they are this component of n plus what? And 2 squared, right? And I can find magnitude of n at any point. Now here, there is no friction. If there was a friction, it is going to be in radial direction because the relative motion is radial direction. And since it's moving radially outward, the friction is going to be the same direction as the spring force. And now it's the time for me to ask you a fundamental question. Well, if you look in the radial direction for this color, the only force in the radial direction is inward. It's opposite of ER, right? So it's a stopping force, basically, right? It doesn't want you to go and increase R. It's a decelerating force. So when the force is decelerating, what do you expect to happen to R dot, which is the radial velocity? So if in the beginning my R dot is 10, when I move in the radial direction, since this spring force is acting opposite to me, I expect to get what? Decelerated, right? So I expect this R dot at R of 2 to be less than R dot at R of 1. So I expect a number that I get at the end to be less than 10. But look, the number that you got is bigger than 10. How can that be? I have a decelerating force, but it seems like my speed is increased instead of decreased. Quite looks like counterintuitive, isn't it? And you might wonder, well, how come? actually, why in the first place does R increase? If the forces are inward, I expect the acceleration to be in this direction. But the problem is this, that in the beginning, first of all, your R dot is not zero. You have a non-zero R dot. You have momentum. So although your acceleration is negative, because you have momentum, you're not going to stop. You're going to keep going. And hopefully in that distance, it is going to bring your speed down. Okay, so that's what makes sense, right? You are driving on the road, you have some speed, and then you apply a brake and it decelerates, but you still keep moving before you can stop. And you expect the same kind of behavior here. Yes, my R can increase because of momentum, but I should get a smaller R dot at the end, but I don't, I get a bigger one. What's the difference between this case and the case that you brake on the road? The difference is this theta dot. Here is not just that you go in one direction, you're also rotating. That rotation is what makes the difference. And where does it show itself? Here, in this term. Okay? Or if you see it here, if you want to see it here, that's where this 4 pi squared is gone to the other side and added to negative 2n. If this term was not there, in other words, the bar was not rotating. If the bar was not rotating, so theta dot was 0, then what would you get for a differential equation? You would get r double dot equal negative 2n r. And if you solve that, you're going to get definitely here a negative number, and so this is going to be a negative on the right hand side, and you end up with a smaller r dot, which completely makes sense. But because of that rotation that you have, this term comes to the other side and is added to negative 2n, and in this case this term is much bigger than 2n. It is what? It is 4 times a little more than 9, so this is around 36, in this case actually 38. So this is 38, that is 20, so this term will dominate the negative and the whole term becomes positive instead of negative. Okay, and because now it kind of like, now my total forces on the left side, instead of being radially negative, are now what? Look, they're radially positive, so my speed is going to increase. And then you might ask yourself, go back to the question that we mentioned. Is this now really a force? So it seems like this is a force that is added to this negative force. This force is a positive force. It's a radially outward force. This force here. How much is it? It is mr omega squared. So it seems like there is a positive force outside which would cancel this and dominate this, and so I get bigger r dots at the end. And what do you call this guy? Yeah, you would call it centrifugal force. So it seems like this is an actual force, but the matter of fact is that's how you justify it if you have your observer sitting on the bar. From an inertial perspective, how would you justify this? The justification is this. These theta dots that you have, these 2 pi radians per second, is too big for the spring to hold. And that radius of 1. Okay, the radius of 1, the initial radius, in the omega of 2 pi is too fast of a rotation along a circular path that this spring force cannot provide that much of centripetal acceleration. So what would you do when you want to go along a traffic circle and the friction of the road does not allow you to go too fast along the traffic circle because it is a small traffic circle? what would you do? You have to bring down your rotational speed, right? You have to bring down your rotational speed if you still want to go along the small traffic circle, because the maximum force you can get from the road is limited. You cannot increase that. So you have to adapt to the condition, right? Look at here. F is equal, the force that you need inward is equal mr omega squared, right? The inward force. And this is fixed. So your left-hand side is fixed and mass is fixed. So the product of this has to be fixed. Okay, so you have to pay attention, or the other way you can look at this term is V squared over R. Or V times omega. There are several ways to look at this. And so, again, where you're going along this traffic circle, if this is really small, right, and you want to go very fast along it, so this V is up and this is your radius R. If this V, you want to keep it as at a high number, okay, and you make this radius very small because it's a small traffic circle, what happens? This goes down, this goes up. So you need a lot of force, and well, you don't have that much of force. So what would you do? If you want to keep your V, which depends on how fast you rotate, right? This V and omega are proportional. So V goes up means omega is going up. If you want to keep that, then you have to increase R. So you have to go along a bigger circle, but typically the traffic circle does not modify itself for you. So what you need to do is you bring down V. Okay, you bring down V, or in this case, you bring down omega. You bring down omega. You don't spin around the circle as fast as you want to. That way you can do it. Now here you say, well, I don't want to change my omega. My omega is fixed at 2 pi radians per second. I'm not going to change this. And this is limited. But this omega is too big. I cannot have equality on the both sides. This force is way bigger than this. So how can I do it? You have to what? In order to bring the right-hand side down and provide equality, you have to bring down your radius. Okay? Yeah? So what does it mean about this case here? What do you think? Let me go back to this equation. Maybe I'm just making it too complicated. I don't know. If I want to, here, let me go up. Let's find the differential equation. Here. If I want this summation of this one and this one to be 0, okay, so I want this guy to be what? 0, and instead of this, I would just write it as omega naught squared. If omega is such that the square of it is 20, then what happens? You get r double dot equals 0, and r double dot of 0 means what? R dot is not going to increase or decrease. So if you don't want your r dot to increase or decrease, how much of omega should you maintain? Square root 20, which is way less than 2 pi. So if I want to spin slower, I would expect my r dot to not increase. If I want to rotate too faster, then I have to what? I have to compress the spring back because I'm spinning too fast and I need a lot of force for that to happen, and this spring force is not giving me that. So what should I do? I compress the spring further back and increase what? This delta L, so I now can get a bigger force out of the spring to make the equilibrium happen. But when you increase the length of the spring, what happens? Your radius is getting bigger. Okay, so this is all the stuff behind it. Maybe I explained it too much. I don't know if I did. Let me know. But in order to visualize this better, what I did is, as I told you, on Canvas, if you go under modules, I wrote this code. And that's this problem I showed you, I guess, last time, problem 1499 animation. So I wrote a code for this, and that code is using this Simulink block called rotating color spring SLX. So that M file sets up the parameters, call the Simulink to solve it, and then give the result back to this for plot and animation. So this can be quite similar to your project, right? So let me show you that. So this is how you set up the problem. You set up K, you set up L, you set up omega naught, you set up M, you set up initial conditions, R naught of 1, R dot at 10, theta dot at 0, right? This is initial theta, not theta dot, sorry. Theta 0 is 0, so you assume you start from horizontal position. Using these, I simulate the Simulink block, which is taking all these parameters in and solving the differential equation. You might say, which differential equation? This one. Here, this guy. It solves this differential equation that we found here. And then it gives you back R and R dot to the workspace so that you can get them, you can plot them, and do whatever you want. Okay, so let me show you that. Now, since your theta dot is constant and your initial theta, you assume it to be 0, then you can find the theta at any other point, right? Because it's just uniform angular motion. Theta of 0 is 0, theta dot is fixed, so theta at any other point is simply omega naught times t plus theta at 0. And that's what you can see here. Constant omega is integrated, given some initial theta 0, and then send out to the oscilloscope and also send out to the workspace for the sake of plot and animation. Now you see here this omega squared is multiplied by r, so I have my term r theta dot squared, which is added to that negative k over rm. Okay? And then this is our double dot. And then our double dot is integrated twice. One time for with r dot of 0 to get r dot, one other time with r of 0 to get you r. And r I will send out to the workspace also. Now some other things that you might look here is I don't let the simulation go all the way until r becomes 3. Why? Because when r becomes 3, it means the length of the spring goes to 0. So you are basically squeezing the spring to absolute 0, which does not happen in real life. So I say the max that you can go and squeeze the spring is to a length of 0.5, which is 3 minus 2.5. So I say as long as you go above 2.5, don't go any further. Physically, you cannot do it, so you stop it. Okay? And you can see I also saturated to never physically also go above 3 for the sake of simulations. And also I would send my r dot out. You can plot it in the scope block and I will send it out. Can you send the variables out to the workspace using the scope block? Yes, I'll show you. So everything is quite clear here, I assume. Please open this and take a look at this. Now, I assume I needed a gain of 1 over m somewhere here. So let me do that. Because m is 1, so nothing is gonna change in this case, but not always. And now I would rotate this block. Remember, Control I, invert a block, Control R, rotate a block. Like that, and then I put it here. There we go. And then I get rid of this text. So here, this is sum of the forces divided by m, so this is R double dot. So it's all set up, everything is good. Now before I run my m file and call this guy to get the data out and do animation, let me show you the thing I said, that with the scope block you can also send your data to the workspace. Because if you remember in the previous session I said you go under syncs and get this block here called what? To workspace, if you want to export your data to the workspace. But that's not the only way. You can directly use the scope block. Really? Yes. Double click on it. Go to the gear, which is the setting. Provide the sample time as much as you want. And then here you go under logging tab. Typically this is off like this in the beginning. You turn it on, you say log data to workspace, give it a name, the format, make it an array, and then what? Okay that. So now when the Simulink block is run, not only I can double click on these and look at them, if I go back to workspace, I see those data are written to the workspace. So let's do it. So here, I set up all my parameters. I call my Simulink using the sim command. I get the data out, and then what? I do the animation. How did I do the animation? I'll show you. Let's first run it, and then I'll show you how to do the animation in this case. There we go. Stops at 2.5. These are your plots of R and R dot. Okay. So these are R. You start at 1 and then you go at 2. Now here everything is versus time. If I want, I can plot R dot versus R. But roughly at what time point R is 2. Now one of the things you can do in MATLAB is to use this guy here called data tip, or in the past we call it data cursor. If you click on this and then come here, get a data point here, you see my y is 2.1 and x is 0.098, and then I can use my arrow and move back as close as possible to 2, which is I guess this point. So roughly at 0.09 seconds I am at r equal 2. And then if I use the same data tip and now click on the R dot plot, by the way, this is R versus R dot. If you want, you can use this bottom one. But I'm just showing you both ways. You click here at the exact same thing and you see you're roughly at what? 12.6. You can do the same thing here. You click roughly at 2, if you can get it R very close to 2, which is here, roughly. You see your R dot should be what? 12.6, which is very close to what we found here. 12.6. Yes? So it is giving you correct result. So these are the plots if you want to see them. And now let's talk about animation. So I want to make sure you really learn MATLAB in this course, especially now that I have some time. Okay, how do you do the animation? So if you see the animation in this case, it's very simple. It's a blue bar that is rotating and a red rectangle that is also maintaining contact and rotating with the bar while increasing its radial distance at the same time. So you have two entities in this plot. One is the red entity or box, the other one is the blue entity. Now, there are commands in MATLAB if you want to draw a rectangle or a circle, and I can show you those as well. But in this case, I use the command line for both of this. And if I just change the thickness of the line, then one of them would look like a box compared to the other one. So you see here, one of them is a line with color 001. 001, these are the components of red, green, and blue, RGB color components. So this is 0 red, 0 green, 1 blue. So this is the blue line. The line width is 4 pixels. The other one is the box, which the color is 100, so red, green, blue, so it is red, and the line width is 10 pixels instead of 4. So clearly this is 10 pixels, this is 4, and it works for me. Now, the first thing I do, I use the command line for both to do what? To basically do the initial plots at the initial angle theta of 0, which is 0. So first thing again I do, I draw the lines at their initial positions or initial configurations. And not only I plot them, I use a handle H1 and H2 for both of these lines so that later I can refer to them and I can what? Modify their X and Y data for the sake of animation. Now, how do I modify them? So if you look at the blue line, the line command, what the line command does, you pass to it X of the endpoints and then what? Y of the endpoints. So the line command syntax is line of x1 and x2 and line of y1 and y2, or you can put x1, x2 in a vector like this and y1 and y2 in a vector like this. Clearly, point x1 is origin, right? This point here, it's at 0 and 0, and that's what I did here. This is x of origin, this is y of origin. Now, where is the endpoint of the bar? Well, the length is L and the angle in general is theta, so X is L cosine theta and Y is what? L sine theta, and that's what you see here. X of endpoint is L cosine, Y of endpoint is L sine of theta for that time point. Right? So very obvious. What about the color? So the color has the same orientation, is theta. The only thing is the beginning of it and the end of it are not at origin or end of the bar. Where is the beginning? Where is the end? So here I considered the length of this color to be 0.2 units. You can change it and make it as long as you want. But here I assume this is 0.2 from left to right. And if I consider the center of this box to be at the position R, then this side here is R minus 0.1 and the other side here is R plus 0.1, and that's what you see here. Okay, now later I'll replace this R naught, which is initial radius, with arbitrary R. Okay, so this is the left edge, this is the right edge, or the bottom edge and the top edge. Okay, yes, and then I have both of them cosine of theta 0. Yes, because these are x1 and x2. So x of a point here and x of a point there are the R minus 0.1 and R plus 0.1, both of them times cosine theta, because they are both x. Similarly, if I multiply by sine theta, those two radii, I would get y of the two ends of that red block. And then I pass a color red, a line width, and now that's color. By the way, I fix my axis so that as it keeps simulating, it does not update it itself, and the frame does not change. The frame stays fixed. So I create a figure, create a title, fix the axis, create the two lines, do a handle, create a handle for them. And now what I do is from II equal 1 to size of R and 1, or if you want, you can say from 2, because the first one is already plotted. So you say from 2 to length of R or size of R, depend on how R is written. Is R 1D or 2D vector? Clearly you see R that exported from Simulink is 2D vector. And you might say, why? So it has two columns. First column 64 numbers, second column 64 numbers. What are those? If you see such a thing, no worries. Let me show you. The first column are the time points, and the second column are what? The actual R values. So if you want to use R values, you should only look at what? Second column of R. If you want to use R dot values, you use what? The second column. The first column is always time. So now, since this is a matrix, not a vector, I cannot use command length. I have to use command size. And when you say size of something and 1, it gives you the number of rows. And when you say size of 2, it gives you the number of columns. So I'm interested in the number of rows or the number of time points. So I say size of R and 1, right? Which is basically the number of time points. What you do is you modify the location of endpoint for the guide, which is L cosine theta and L sine theta. But theta is not the original theta anymore, it's the current theta. And the current theta at any point, I always get back from what? My Simulink. You see? My theta is similar to R, it's a 2D thing. It's a 64 by 2, and these numbers here in the second column are theta at any point. So now I use the initial theta, now I need the second theta. So where should I go? Row number 2, column number 2. Row number 3, column number 2, right? And that's what I do here. I'm looking at row number I. Why? Because my loop counter is I in general. And then what? Column number 2. And by the way, I'm using sine and cosine, not sine D and cosine D, because the theta I exported is in radians. So I get my endpoint for the guide, and then I update my X and Y data, which is this. This is X data of handle H1, and this is what? Y data of handle H1. I update both of these. Clearly, number 0 never needs updating because that's always fixed at origin. It's the other end of the bar that needs updating. And instead of theta naught, I use what? The new theta. So you see, I'm not modifying this end, I'm just modifying the other end, which has rotated, and I got those numbers from the top equation. So now here, this is gonna rotate my blue guide to the new orientation. Then I modify, you can see R minus 1 and plus 1, and sine and cosine of theta. I modified the two endpoints of the red color, and then I would update my X data and Y data of the handle for the red color here. And whenever I updated my data, I say what? Draw now. I'll talk about this refresh data in a second. I say draw now. And draw now, what it does is basically updates the data. So what is this refresh data? It just tries to basically keeps the new data and get rid of the old data, and basically not, there is also the command flush data, which basically you try to update the data. Even if you don't do refresh data, it still works. Okay, and let me now show you one more time. There we go. Yes? And if by any means this is too fast, remember what you need to do, right? Use the command pause. You say pause 0.01 seconds. This creates a little pause in the loop and make the update a little slower so we can see better. Yes, if it's still too fast, make it 0.1, it's going to be quite slower. So this is how you control the speed of animation. Yes, and all you need is draw now. Now, as I said, refresh data, which let's take a look at it together. So whenever we don't know what any command is doing, the best way is, as always, MATLAB help, right? If you're not sure about it, so say refresh, and it's all one word. So updates the chart data in the current figure to reflect the changes in workspace variables. Before that, you must first set the data source properties, which we did using the command set. Okay? So that's refresh data, just refreshing the data. And this is really good when basically, let's say here you want to update a XY plot and change the frequency and keep updating the whole plot, all of the points on it, instead of just like one endpoint. This really shows itself. Okay? And as I said, you have the command draw now. Which updates the figure and processes with callbacks. Okay, so if you want to see the figure immediately, so this is for figure, but refresh data is just for data. So that's the difference. Refresh data does not basically update the figure, it updates the data. But as I said, for simple cases that you use the command set, you really do not need to use refresh data. But if you want the animation to happen, you need draw now. And then there is the command, let's see, flush and flush data. This is a good one. If your animation has a huge number of data points and it is a heavy animation, I absolutely recommend you use the command flush data. And flush data all. This would get rid of the previous data used in the previous loop counter for the animation, and your memory is not going to be overloaded and your program crashes.